Okay, so this is going to be part 2 of my 10 hardest GCSE maths questions series. So just looking at part 1 quickly, if you haven't seen this video already, I will link it in the description. But if you have a look on the screen, you can see if you go into the description of the video, and it'll be the same on this one, click into that description and have a look, and you'll see that I link all of the topics that you need in order to access the majority of these questions. Now, a lot of them, obviously via the very nature of the question, are very unique, but I will link any topics that you need in order to be able to access them. It might not be in those videos that I'm specifically explaining how to answer that exact question, but they will be all of the sort of topics behind that question that you need to know. So there you go. If you haven't already, don't forget to check out part 1, but let's get started with part 2. Okay, so looking at our first question, we're looking at some indices with algebra. Now, a lot of these questions are obviously subjective as to whether you find them difficult or not, and it might be that you're brilliant with indices, so this might not be a super difficult question for you. But I have started off with what I would say is the easiest question out of the 10, but there is a reason behind it. Now, indices as a topic is generally around about a grade 6 up to a grade 7, depending on the nature of the question. But these style of questions are very difficult. So these difficult indice problems, particularly with algebra, just tend to throw students quite a lot in the exams. They don't look nice, they're not particularly nice, but there is relatively nice ways that you can go about them. Now, with these types of questions here, the first thing that we need to look at is the base numbers. As we already know, when it comes to indices, if the base number, or a letter, if it's a letter type of indice question, as long as that's the same, we can apply our laws of indices. So for example, if we had something like 3 to the power of 2, multiplied by 3 to the power of 5, you can add those powers and get 3 to the power of 7. But if that base number's not the same, you can't apply those rules. So we are going to be looking to make the base numbers the same, no matter how difficult this question looks. So it says 9 to the power of a half is equal to 27 to the power of a quarter divided by 3 to the power of x plus 1. And it wants us to find the exact value of x. Now, we may have to make an equation, we may not, we may just be able to use the equation we've got here, but ultimately we want to make those base numbers the same. And if we look at the 9, the 27 and the 3, they are all powers of 3. 9 is 3 squared, so we could write 9 equals 3 squared just over here as a reminder, and 27 is 3 cubed, or 3 to the power of 3. So if I break this down into its base numbers of 3, 9 to the power of a half, I could write the 9 as 3 squared, and if I put that in brackets to its original power, that would be to the power of a half, and we'll deal with that in just a moment. That is equal to 27, and we know that 27 is 3 cubed. Again, I'll put that in brackets to its original power, which was a quarter. That's not a quarter. Let's get the right fraction there, a quarter. And then that's going to be divided by 3 to the power of x plus 1. I don't need to change the 3 because it's already in that base number 3 that we're looking for. So there we go. Now, when it comes to these now, we should hopefully know that powers in brackets can be multiplied. So I can do 2 times this minus a half. 2 times a half is just 1, so that'd be 2 to the power of 2 times the minus a half would be to the power overall of minus 1. So that'd be 3 to the power of minus 1, and what's that going to be equal to? On the next one, we have a power of 3 that we need to multiply by the power of a quarter. That's just going to multiply the numerator, so that's going to be 3 to the power of 3 over 4, and we're dividing that by 3 to the power of x plus 1. Now, there's a couple of different things that you could do in this situation. We want to look for the easiest route. We know that when we're dividing, what we can actually do is subtract the powers. But do I really want to do 3/4 take away the x plus 1? Maybe not. There are a couple of different ways that we could look at this. I think one of the easiest ways to do this is to actually multiply both sides by this 3 to the power of x plus 1 and basically move that to the left hand side of the equal sign. So if I multiply by 3 to the power of x plus 1 and do that to both sides, multiply by 3 to the power of x plus 1, we would have 3 to the power of negative 1 multiplied by 3 to the power of x plus 1, and that equals 3 to the power of 3/4. Now why would I do that? Because actually if I was going to do a takeaway, what I don't want to get wrong is the fact that I'm taking away both of those pieces in the x plus 1. So I could miss something there, whereas I know if I'm going to do a times here with my powers, which means that I'm going to add my powers, I'm less likely to make a mistake. And actually adding these powers together, -1 add x plus 1, is pretty easy to do. -1 add the 1 would cancel out, so that would just be 3 to the power of x. So we end up with 3 to the power of x, that's all cancelled out really nicely, and that's equal to 3 to the power of 3/4. And we've pretty much solved that there, because if 3 to the power of x is equal to 3 to the power of 3/4, then we know that our x value in our power is going to have to be that 3/4 there. So we know that x is equal to 3/4. And there we go, that'll be our final answer for that question. So there we go, there's our first question. Hopefully you found that a relatively nice one, just to ease you into these 10 questions. Let's have a look at our next one, because they are going to start to get quite a bit trickier from here. Okay, so looking at this question here, where we are sketching graphs, we're doing some solving quadratics, we're doing completing the square, we're looking at turning points, y-intercepts, and everything to do with coordinate geometry. So this is quite a big step up from the last question, but again, if you're really good at completing the square and sketching quadratics, this again might not be the most difficult for you, but this is a pretty tough question. So looking at this, it says sketch the graph of y equals 2x squared minus 8x minus 5. And already it's a difficult one because you have that 2 in front of the x squared, and finding the turning point of that is a little bit trickier than normal. Showing the coordinates of the turning point and the exact coordinates of any intercepts with the coordinate axes. So again, we are doing this non-calculator, and this is an exact coordinate question. So we're going to be using, potentially, we'll wait and see, some surds in these actual coordinates. So it doesn't really matter what we start with. I would probably start here by drawing or finding the turning point. Now if we find the turning point, we need to complete the square. With a 2x squared, we're going to have to first factorise out that 2 before we go about completing the square. Well, that's our first step in completing the square with harder quadratics. So if we do that, we would have y is equal to, we'd have 2 on the outside, and then we just have an x squared minus 4x, and then that's going to be minus, and you can either write this as a decimal. I prefer to keep it as fractions. I'm going to write it as 5/2. If you want to keep that as 2.5, that's fine. Now we need to actually complete the square. So to do that, I halve the coefficient of x. So we're going to have 2 lots of, I'm just going to actually do the completing the square part first. I'll bring that 2 back in just a moment. So we'll have x minus 2, when we halve that 4, that's going to be squared. And then we need to expand that, obviously, or think about what that would be expanded in order to complete the square. So if we did expand that, we'd get a plus 4 at the end. Now we don't want plus 4 at the end, we want minus 5/2, or minus 2.5. And again, if I put minus 2.5 up here, it might be a bit easier to visualise that. So how do we get from positive 4 to negative 2.5? Well, to do that, we'd have to take away the 4 to get to 0, and another 2.5, so that'd be minus 6.5. And that's that middle part, we've completed the square. Now of course we have a 2 on the outside, so I can't forget about the 2. I have to put in another bracket. You can either use a bigger bracket or you can put in a square bracket, it doesn't really matter, but we have to reincorporate that 2 on the outside. Once we've done that, you've got to multiply that 2 back in, so 2 lots of the x minus 2 squared we can just write as 2 lots of x minus 2 squared. And that negative 6.5, we can actually multiply that by 2. So 2 times negative 6.5 will be negative 13. We have now completed the square. So now we've completed the square, we can write what the minimum point is, or the turning point. And we get that from this value inside the bracket and this value just at the end there. And hopefully you know, and if you don't, obviously the video is linked in the description, that the x coordinate there, we flip the symbol, so that would be positive 2. And the y coordinate, we keep the symbol with that, so minus 13. And that right there is our turning point. Okay, there we go. So turning point, or you could label that as the minimum point for this one. So there's our turning point. Now we just need to think about what we could find next. Now it's completely up to you. One of the easy things to find on this is the y-intercept. The y-intercept is that number up here at the end of our equation there. So our y-intercept, there we go, if we label that there, the y-intercept would be -5, or we could write that as a coordinate. X is 0, y is -5, so 0, -5. Okay, on to the next part. So to get our solutions, or in other words, the point where it crosses the x-axis, I'm going to have to think about solving our quadratic. Now to do that, we're going to solve it when y is equal to 0. If we think about sketching a basic axis, just to think about what this might look like, we know that the solutions, however this looks, I'm going to get rid of this, but if I was to draw a little basic sketch like that, we know our solutions are here and here, and they are on the x-axis where y is equal to 0. So if we don't actually know what it's going to look like yet, but I'll leave the axes there. So when y is 0, we can say that this equation that we've completed the square for is equal to 0. And if I write that, I can say 2 lots of x minus 2 squared, take away 13, is equal to 0. And I just need to go about solving that. It's not actually too difficult to solve once we've completed the square. If anything, sometimes it's a little bit more efficient than plugging it all into, say, the quadratic formula or something like that. So to solve this, I'll add 13 to both sides to start with. And that would give me 2 lots of the x minus 2 squared is going to be equal to positive 13 when we add 13 to the other side. I've now got to think about what to get rid of next. I'm going to get rid of that multiplication by 2 there, so I'm going to divide by 2. We already know what that is, divided by 2, because we did it earlier. It's going to be 6.5. So if I divide by 2, we're going to get x minus 2 in brackets squared is equal to 6.5. Now we can move on to the next step. So the next step, we're going to have to get rid of this squared bracket here. So to get rid of that squared bracket, we're going to have to square root both sides, and this is where we need to be really careful. If we square root the left, that's fine. It gets rid of the fact that it's squared, so x minus 2. But on the right there, if we square root 6.5, there is a positive and a negative value for that. So I have to incorporate that by putting it's going to be the plus or minus version of the square root of 6.5. And there we go, we're almost done. The final step here, I'm going to have to bring this up over to the top. So the final step will be to add that 2 to both sides. So if we add the 2, and you can put that before or after the square root. I'm going to put it before. So I'm going to say x is equal to plus 2 or positive 2 plus and minus the square root of 6.5, and that's our 2 solutions there. So we've got one solution which is 2 plus the square root of 6.5, and we have another solution which is 2 minus the square root of 6.5. So we need to think about what this is going to look like. We have 3 things that we need to draw. We have our y-intercept, we have our turning point, and we have our 2 solutions. So technically that's 4 things we need to draw. So let's think about actually drawing that. We know that this is our y-axis and this is our x-axis, but what's it going to look like? Well, the y-intercept 0, -5 is going to be below the axis, so let's sort of draw that on down here. Again, this doesn't need to be perfectly scaled, but I'll label that as -5. We know that our turning point is going to be 2 and -13, so that's going to be to the right on the x-axis, and it's going to be lower than that -5. So this isn't ideal the way that I've drawn it, because I'm going to have to put my -13 somewhere like that, which clearly is not scaled very well, but that's fine because it's just a sketch. So we'd label that as 2 and -13, and that's our turning point. And you can probably already tell then that our solutions, we're going to have one positive and one negative. Let's think about why. 2 plus the square root of 6.5 is clearly going to be a positive number. The square root of 6.5 is somewhere between the square root of 4 and the square root of 9. So let's imagine that's something like 2.5. And we're going to have to figure out then, so 2 plus 2.5 would be around about 4.5. And 2 take away 2.5 would be around -0.5 or something like that. Okay, a complete guess, of course, because we're just making an estimate there. But that means I know that one of them is going to be negative, so here somewhere, and that is going to be, let's just label it to the left so it doesn't get in the way of my curve, 2 minus the square root of 6.5, And on the right, let's say it goes here somewhere, and that will be 2 plus the square root of 6.5. And there we go, there's our coordinates. So I do actually need to sketch that curve in. I need to try and make it a nice smooth curve. There we go, it might have been easier to draw the curve first. Oh, there we go, and I've just missed that point. So if I just get rid of my cross as it's my sketch, there we go. And then let's just put the cross there. There we go. And I'm quite happy with that sketch there. So we've sketched that on, we've done completing the square for harder quadratics. We have used completing the square to solve a quadratic and also had an understanding of the turning points. But there we go, there is a sketch. And again, remember you are only doing a sketch of the graph. So it doesn't need to be perfect, it doesn't need to be perfectly scaled. It just needs to show what it's going to look like as a sketch. So there we go, there's question 2. Let's have a look at our next question. Okay, so this question is some more coordinate geometry, although this question is more focused on equations of lines and perpendicular lines, more so than our last question, where we were looking at sort of a quadratic and turning points. This is more about straight line graphs. So this one here, it says the straight line L has the equation 3x plus 2y is equal to 17. Point A has the coordinate 0, 2, which you may or may not recognise, that's actually a y-intercept equation. And the straight line M is perpendicular to L and passes through that point A. Line L crosses the y-axis at point B, and line L and M intersect at point C. So that's just given us some letters to talk about where they intersect and stuff like that. Work out the area of triangle ABC and you must show all your working. Well, we're going to have to think about what this looks like, and essentially I think we're going to have to draw a sketch of this one as well. But to do that, let's first have a look at this first equation. Think about what that would look like. When we know that all line equations, we want them in the form y equals mx plus c. So I'm going to start by minusing that 3x to the other side. And if I do that, I'll put minus 3x here, but we would have 2y will be equal to, and I want it in the form mx plus c, so I'm going to put my minus 3x here, and then introduce a plus symbol in front of that 17 as it was a positive 17. You don't have to do that, I just prefer to keep it in that order. Now I want to divide both sides by 2 because I want it to be y equals, not 2y equals. So that would be y equals minus 3 divided by 2, which I'll write as a fraction, 3 over 2x, plus, and then I could write that as 17 over 2. Okay, you could divide that if you want, but I'm not really going to need to know exactly what that decimal is there just yet. So let's leave that as 17 over 2. There is the equation of my first line. And if I think about what that looks like, if I was to draw sort of a basic set of coordinates, again, just doing a sketch, and this is just to help me, I'm not going to gain marks for this, but I might need it. It's got a negative gradient, and it's got a y-intercept of 17 over 2. Now, to be fair, 17 over 2, that's 8.5. So let's imagine that's up here. Let's just label that 17 over 2. Or 8.5, and I have a negative gradient. That negative gradient is 3 over 2, or 1.5. That's relatively steep, but let's just draw something in like that, and there we go. Let's imagine that is what the line looks like. So that's where I'm at the moment. I know what the first line looks like, I know what the gradient is, I know what the y-intercept is. Now we are moving on to this next line. So the straight line M is perpendicular to L, and it passes through this point 0, 2. So if we go about drawing that line for our second equation, now the gradient of our first line, M, was equal to that negative 3 over 2. That was our gradient there. And we're now looking at a perpendicular line. So we want to use the negative reciprocal. So the gradient of the perpendicular line is going to be positive 2 over 3, flipping it over and changing the sign. And if I put that into a line equation, we'd have y equals 2/3 x plus c. And in order to find the full equation, we need one of the coordinates. Well, that's fine because it told us that that passed through the coordinate 0, 2, just up there in that second line. So you can sub that all in if you want, but if you know that that's the y-intercept, we can actually just replace the c with the 2. We don't need to write it or substitute those values in as much as we would if it was, say, 1, 2 or something like that. So we know that the equation is going to be y equals 2/3 x plus 2, and there is our second line equation. It does say that that crosses through the point B on the y-axis. Sorry, that's line L crosses through the point B, so actually we could have labelled this as point B to avoid the confusion that I almost had just then. And then it says lines L and M intersect at point C. So if we draw this, we'll find where point C is or what it's going to look like. So let's imagine coordinate 2 is just there, and this has a positive gradient of 2/3. That's less steep than my last line. So something that looks like that. There we go. So it said that L and M intersect at point C. So this here is our point C. And were there any other letters we were given? We had point A was the coordinate 0, 2. So this one here is A. And that was all the letters we've got. So the question said, find the area or work out the area of ABC. So let's think about how we would actually do that. So here is the triangle ABC, this one just here. I don't want to draw over it too much, but that's the triangle we need to get the area of. To work out the area of a triangle, we just want to do half base times height. So let's think about what this base would be. Obviously it's on its side, but this here could be our base. So obviously any side could be the base, but that there is the base. So this 17/2, at this point probably would have been nicer for me to write that as 8.5. A little bit quicker for me to find the distance between them. So from 8.5 to 2, that has a base of 6.5. So there's the base. I just need to times that by the height. The height is the perpendicular height, so from the y-axis leading up to that C coordinate just there. So if I knew the x coordinate of where they cross over, then I would know the height of the triangle and I could work out the area. At the moment we don't know that coordinate though. So the maths that we have to use to find where lines intersect, we have to solve them simultaneously. But because they are both equal to y, we have y equals 2/3 x plus 2, and y equals negative 3/2x plus 17/2, what I can actually do is just set them equal to one another. So if I take this equation here, and I take this part of the equation there, and just set those equal to each other in either order. So I'll put that first equation first, so minus 3/2x plus 17/2, and that is going to have to equal 2/3 x plus 2. And there we go. So we need to actually go about solving this. Now there's lots of different ways that you could solve it. You could just go about adding the fractions and subtracting either side like we normally do. I am going to actually remove the fractions. So I'm going to multiply both sides by 2, which will eliminate this divide by 2. And it'll also change these numbers here, so it's going to change the numerator and that 2 at the end. But that's fine. It just makes it slightly easier for me to deal with. So that would be minus 3x plus 17 is equal to 4/3 x, timesing that by 2, plus 4. I can do the same to get rid of this 3 on the bottom, so we can times both sides by 3. So let's times by 3, and we're just going to have all nice whole numbers. So that would be negative 9x plus 17 times 3 is 51. And that is equal to now 4x plus 12. There we go. You just got to make sure you multiply everything there by the 3. That is a much nicer equation to solve now. We can probably solve that quite nicely. If I add 9x to the other side, that would be 13x. I'm going to do this in one step. I'm going to also subtract 12 from the other side, and that equals 39. So there we go. That's a really nice equation to solve now, because we can just divide both sides by 13, and when I do that I get x is equal to 3. There we go, so x is equal to 3. Now that's quite a key coordinate there. You could, if you wanted to, sub that back in and go about finding the y coordinate, but does it actually help us in this question? Let's just have a look. Let's see if we can answer it without subbing it in, because we don't want to make more work for ourselves. Now as it turns out, that then is the height. So why would I bother subbing it back in? I've got the base, I've got the height, I've got everything I need to work out the area of the triangle. So let's just work out the area. So the area of a triangle is half base times height. So I'm going to have the area is equal to 1/2 multiplied by the base, which is 6.5. You can put a times sign or put them in brackets. And we're going to multiply that then by the 3. So 1/2 times 6.5 times 3. Again, take your time to work that out. A half multiplied by 3 will be 1.5, or you could times it by the 6.5. So you just got to do 6.5 multiplied by 1.5, and you can type that into your calculator. So that is 9.75, and that is the area. There we go. It doesn't give us any units, so you could write something along the lines of units squared, but you don't necessarily need to. When we're not given any units, we can just write that numerical area. So 9.75, again, would be our final answer. So there we go. There is some really, really nasty coordinate geometry there, looking at rearranging the equation of a line, then looking at perpendicular lines, using simultaneous equations to find a crossover point, and relaying that and sort of applying it to a diagram that you've had to sketch to find the area of a triangle. A really nasty question, but there we go. There is question 3. Let's have a look at our next one. Okay, so on to our next question. Here we've got something that looks horrible. We have a cone and we have this kind of strange sector drawn on the left. It says the diagram shows a sector of a circle with centre 0, which we can see on the left, and the point C is the midpoint of the arc AB. The diagram also shows a hollow cone with vertex O, and the cone is formed by joining OA and OB. So on the left here, this OA and OB, if we were to join them together and kind of push this circular sector into a kind of upwards into a cone shape, which is very hard to visualise, it would form a cone. The only way to really visualise this question would be to actually get a hollow cone, cut it from one point here up to the vertex and unravel it, and you'd see that if you unravelled it perfectly, it would make the shape that we've got on the left there. But that's very hard to visualise. So this O here is the vertex, and you can see A and B down there are sort of joined together. So it's not very nice, and that's very hard to visualise, but if you're really struggling to visualise that, maybe just cut out a bit of a sector and push it together, and you'll see it will make a cone shape. It tells us down here the cone has a volume of 56.8 and a height of 3.6. Calculate the size of angle AOB of the sector and give it to 3 significant figures. So AOB of the sector OACB is actually the larger angle as well. So actually, they're really nasty there. They've tried to even throw with the angle, because immediately you kind of think, oh, okay, that must be this angle here. But actually, it's the sector OACB, which is all the way around, because it goes from A to C to B around the outside of the major sector there. So this is the angle we're trying to find. So we could call that angle X or theta or whatever we want to call it. Let's call it theta. So how are we going to approach this? Well, we've been given the volume of a cone formula, we've been given the curved surface area of a cone, and we're going to be working out the angle in a sector, which has its own formula. So we're just going to have to sort of go for this and think, what can we work out to start with? Well, we've been told the volume is 56.8, so we must be able to work out something from that. And our volume formula is up here, 1/3 pi r squared h. So we know pi, we know the radius. Actually, no, we don't know the radius, but we do know the height. We're given the height here, 3.6. So if we label that on our cone, the height there is 3.6. And we're going to have to plug in all the values to find the radius. Definitely going to need a calculator for this one. So you want your calculators at the ready. So if we're plugging these values in then, if we plug it into our volume of a cone formula, we've got the volume, which is 56.8, and that is equal to 1/3 multiplied by pi, multiplied by the radius squared, multiplied by 3.6. So to get r squared on its own, we're going to want to divide by all 3 pieces. So 1/3 times pi times 3.6. And we can do that in one jump. We just have 56.8 divided by 1/3 times pi times 3.6. And that will be equal to r squared. So if we type all of that into our calculator, 56.8 on the top, and then 1/3 times pi times 3.6 on the bottom, and that comes out as 15.066666795. So r squared is equal to 15.0466795. And to get the value of r, we want to square root that. So if we square root our answer, so square root answer on the calculator, we get 3.8815805999. And there's our radius. So we've managed to figure something out. How's that going to help us? Well, now let's think about what we're actually trying to work out. So we're trying to work out this angle in the sector. If we knew the area of this sector, then we'd be able to use the radius and we'd be able to reverse that to figure out the angle. Because we know when we're finding the area of a sector, to get the area, we do the area of a circle, pi r squared, we now know the area, and we'd multiply that by the angle out of 360. So to find that angle, we just need to know what the area is. And the area of that part that I've shaded in, that is the curved surface area of our cone. So let's look at our curved surface area formula. So for the curved surface area, we have pi times r times L. Do we have that value L? Now if we think about this in terms of the inside of a cone, how do we find that length? Going from the top to the bottom, right down to the centre of that circle, we know that that's 3.6. We also know, going to the right or the left, what the radius is. If I round that for the moment, that's 3.88. So inside there, that is a right angled triangle, and we are missing the hypotenuse, which is our L. So to find that length L, which is also going to be the radius of our sector, then we actually need to go about doing a bit of Pythagoras. So if we do a squared plus b squared equals c squared, or in this case L squared, we'd have 3.6 squared plus 3.8815 etc. squared, and that's going to equal L squared. Now I already have that 3.88 number on my calculator, so I'm going to type in 3.6 squared plus answer squared, or if you didn't have it in there, you'd have to type it all out again, and that equals, and here we go, we've got L squared is going to equal 28.06666795. And you could probably actually get away with not writing down all these decimals, as it does only want it to 3 significant figures. It would probably be fine to write it to 5 or 6. But that's L squared. I want to know the value of L, so again I want to square root that, so I'm just going to type in square root answer, and I get the length L is equal to 5.29402196. And there we go, we've found out something else. That L there, that is the radius of our sector, which seems a little bit strange because we had the radius of the base being 3.88, and we don't want to get that confused with the radius on the sector, because that radius on the base is actually just part of the distance between the curved part of our sector, so not actually that radius there. If you think about, again, visualizing how that would be created, if you pulled that A and B together and poked the middle up into the vertex of the cone, that would actually be the length L there, that sort of slanted length. So we need to go about using the correct numbers there. So we do have our radius now, which is the length L. We have, well, we already know what pi is. We just need to find our angle. So now is when we're going to use this formula. So area equals pi r squared multiplied by theta over 360. So if we start plugging that in, we've got the area is going to be equal to pi multiplied by this 5.29 number. I'm not going to write it all down. Squared multiplied by the angle, which I'll call theta again, over 360. Now, we do have the area. We can get the area by working out the curved surface area, which is the formula that we were actually looking at just a second ago, this curved surface area. So although at the moment we're missing two pieces, because we have the missing angle theta and we have the missing area, we can actually get that value for the area. So if I get rid of that word area there, and we actually work that out, to get the curved surface area, it's pi times r times L, which is pi times the radius of the cone, 3.88, and then multiplied by the L number, which is 5.29, and let's see what that equals. Now I'm actually going to use the full numbers that I've worked out, so I'm going to do pi multiplied by the 3.881580.599 multiplied by the full 5.29 number, which was already in my calculator, so I'll press answer. So that equals 64.55 and some more decimals. So 64.55713,006. There we go, and that's the area there of the cone. Okay, and that's in centimetres, so we can say that's centimetres squared. There we go. So that's my curved surface area. That can now go at the front of my formula. So that could be 64.55713, and a few more numbers there. I won't write down the whole thing. So to start to rearrange this, just like before, I can divide both sides by what's next to my unknown, these bits here, and that will give me theta over 360. So that'd be 64.55713, all divided by pi times 5.29 squared, and that equals theta over 360. I'm almost running out of space. So let's actually work that out. 64.55713. I think I need to necessarily write the 006 in, that's not going to make much difference now. And then divided by pi times 5.294021906 squared. Click equals. And there we go, that gives us 0.7332 and some more numbers, and that equals theta over 360. Okay, so I've got one more step, because I've now just got to multiply by 360, and that will give me the full angle, and we'll actually be finished there. So I'm running out of quite a lot of space, so let's just try and move something out of the way. Let's try and move this out of the way. There we go. So for the final step, multiply both sides by 360. That'll give us theta on its own. Multiply by 360. So that number on my calculator, just press times by 360. And I get my final answer. I've got theta is equal to, and I get 263.95 and a few more decimals, but I'm going to stop there because I remember it wanted my answer to 3 significant figures, and if I round that to 3 significant figures, I get 264 degrees regardless of the next decimals there. Right, I better highlight that because there's a lot of working out for this question. So there we go, 264 degrees. So thinking about the topics that we've had to do there, we've had to do reversing the formula for the volume of a cone to find the radius. We then had to use Pythagoras' theorem to get the length on the outside of the cone. That allowed us to get the area of the sector by doing the curved surface area of the cone. We then plugged that into the area of a sector formula, reversed that, and found the angle. So as you can see, that's a pretty full-on question. There's a lot of working out there. I've had to fill up the entire screen with working out. But there we go. There is another question. Let's have a look at our next one. Okay, so our next question is looking at vector proof. And to be fair, none of these videos would be complete without a vector proof because they are pretty nasty questions. Now this one isn't the worst vector proof that's ever come up on the GCSE, but it is a pretty nasty one. And as I said, obviously part 1 I went over some pretty nasty vector proofs as well. So looking at this one then, let's just have a think about what we're going to need to do. So it says P is the point on OX such that O to P, P to X is 1 to 2. So going across there, it says that O to X is the vector A. And if we split that up into this ratio, that's 1/3 and 2/3. So O to P would be 1/3 A, and P to X would be 2/3 A. And that's splitting up that first bit. If we look at the next part, we're told that O to R, R to Y is 1 to 3. And we're told that O to Y in total is B. So O to R, and this ratio is 1 to 3, so that's 1/4. So that would be 1/4 B. and this would be 3/4 b. And that's all the vectors that we've been given there. It says work out in its simplest form the ratio z to p, z to r. Z to p is the full length of this line, so I want to know what the full length of that line is as a vector. And the other part is z to r, and z to r is just this part of the line. So we have two vectors to work out, the full length of that line and also just z to r. Actually working those out isn't overly difficult in terms of the context of vector proofs here. It's not the most awful question. So to get from z to p, I might first want to know how to work out one of these missing lines. So z to o would be a good one, which is the same as y to x. So they're the same vector, but let's work out z to o. Now to get from z to o, let's think about the journey of the vectors that we have. We know the top here is the same as the bottom, as it is a parallelogram. So all the way across the top would be 1a. We also know that to get from y to o, the opposite direction, that's just a movement of b, or in the case of going from y down to o, that would be minus b. So to get from z to o, I'd have to go all the way across to y, which would be a. Let's write this down. So the vector z to o would equal a, and then we'd have to go minus b, because moving up the line there is a plus b, so we're going backwards, so a minus b. So to get from z to o, we've got the vector a minus b. Now I can get from z to o, I can get from z to p, because I can get from z to o using the vector a minus b, and then we've also got a third a there that we'd add on. So for that vector z to p, that would be a minus b, and then add a third a. And if we combine those a's there, collect those like terms, a plus a third a, if we write that in terms of thirds, that'd be 3/3, add 1/3, so that would be 4/3 a minus b. Or you could always write those the other way around. I tend to try and keep the negative symbol after if I can, but you could write that as minus b plus 4/3 a. And there we go, that's our first vector. So that's going to be an important one. I'm going to underline that so I don't forget to use that one. So there's the vector z to p. I've done the one on the left. I just need to do the one on the right. So now we define the vector z to r. So to get from z to r, very similar of how we got from z to p, I'd still go from z to o, and then I'd go up from z to r. So that one there, again, you could break this down as z to o first. I already know what z to o is, so I'm just going to write z to r. So z to r is that original vector a minus b, and then we're going to add on to that a quarter b. So a quarter b gets us that last little bit from o to r. Again, I need to simplify this. So if I simplify that, I've only got the 1a when I collect the like terms, but I've got a minus b plus a quarter b. Thinking about that in terms of quarters, minus b is minus 4/4 b. Add a quarter to that, we'd have minus 3/4 b. There we go, so a minus 3/4 b. And there is our second vector. Now, that vector z to r is the smaller part of the line. So if we think about this vector, 4/3 a minus b being the full length, and I'll write that as the full length. There we go, and this vector here is only part of that. So it should be a fractional amount of 4/3 a minus b. Or in other words, if we factorise it, we should get, hopefully, 4/3 a. Now looking at this vector down below, if we want the b's to match, let's just highlight that. We've got minus b here, but here we have minus 3/4 b. So if I actually go about simplifying that by factorising 3/4 out, hopefully it's going to match what we have above. That's not the easiest to do, but let's try it out. So we get 3/4 on the outside. What we're going to get on the inside? Well, a divided by 3/4, let's leave that for the moment, because we know that 3/4 divided by 3/4 gives us the 1b, which is what we're looking for. So it might be that to the side we just want to do 1 divided by 3/4. So 1 divided by 3/4 is the same as 1 multiplied by the reciprocal, 4/3, so that is equal to 4/3. So when I factorise 3/4 out, I actually get 4/3 a in this position. And then looking at those vectors, they actually match. So the one at the top, Z to P was 4/3 A minus B. Z to R that we've just worked out is 3/4 of 4/3 A minus B. So we have both of those having that matching vector there. So where it says work out in its simplest form the ratio Z to P, Z to R, well, if we think about writing that down, Z to P and Z to R, Z to P was the full length of the line, and that was one lot of the vector, although we didn't need to factorise one out, it was just one lot of 4/3 A minus B. And Z to P was 3/4 of that vector, so that's 1 to 3/4. Now when we're writing a ratio, we don't leave fractions unless we're specifically being asked to leave a fraction there. So when we write this ratio, we want to make sure that we get whole numbers. So what do we multiply by to remove that dividing by 4? Well, we just multiply both sides by 4. 1 multiplied by 4 is 4, and 3/4 multiplied by 4 just removes that divide by 4 below the 3, so 4 to 3. So our final answer for this one is 4 to 3, and there we go, that would be our final ratio. So there we go. Obviously that is a tricky question. I'm under no illusion, vectors is not an easy topic, but in terms of some of the vector questions, and again I will link in the description a video with all of them that had sort of like the hardest vector questions. In terms of some of those, this one isn't quite as bad as some of the ones that have appeared in the past. But there we go, there is a vector proof question, always a tricky topic. Let's have a look at our next one. Okay, so on to our next question. We've got circle sectors and circles with algebraic lengths, and the question is asking us to find the value of x. So it says here, shape A is formed by removing a sector of a circle with radius 3x minus 1 from a sector of a circle with radius 5x minus 1. So this is the little sector that's being removed, this one just here. So when we remove that, it says that the area of that is equal to the area of B. It says shape B is a circle with diameter 2 minus 2x. So we need to find the area of these parts in terms of algebra, and then we're going to have to solve it. And chances are we're going to have some form of quadratic equation. So let's just have a look at what we know. So we know that the large sector has a radius of 5x minus 1. It does actually tell us that in the question, but if it didn't, we could just add together those other two lengths there. We've got the 3x minus 1 and the 2x. And we have the circle over here where we've been given the diameter. Of course, if we're looking at area, we only want to know the radius, so half of that would be 1 minus 1x, or just 1 minus x. So that's what we've got so far in terms of our algebraic lengths. We know that the area of a circle is pi r squared. So the area is equal to pi r squared, and if there is an angle involved, we'd also have to multiply that by the angle over 360. So that's the area of a sector. So let's just have a think about what we've got to do. Well, in terms of the area of A, we need to get the area of the large part of the sector using the full radius, and then the area of this smaller sector just here. We'd have to take them away from one another. So if we write that down, let's write down the area of A. So the area of A will be equal to, and we do pi multiplied by the radius squared. Let's just put that in brackets. So the radius of the large shape is 5x minus 1, and we are squaring that. And that is also going to need to be multiplied by 45 over 360. So actually, we could probably put that at the front. That would probably be a little bit nicer. Let's put the 45 over 360 there. So 45 over 360 pi multiplied by the radius squared, and we need to subtract the smaller sector, which would work out in very much the same way. 45 over 360 pi, and the radius of that circle, which is 3x minus 1 squared. Right, so that is going to give us the area of A. For the area of B, let's write this up here, the area of B, that's going to equal, thankfully no angles in this one, it's a full circle, but it is going to be pi multiplied by the radius squared, so 1 minus x squared. So how are we going to go about figuring all of this out? You could from here go about expanding them all first but I think what's a little bit nicer to do is just to actually bring the sort of all the pi's together and set our equation, because there's a few bits that look like they're going to cancel out. So what I mean by that is if we write the area of A, and bearing in mind they both have this 45 over 360 pi, which we could kind of factorise out to the start. You could leave them in separately if you want, but we can say that 45 over 360 pi multiplied by, and let's think about how we'd write this, we'd have to put another set of brackets in because we have 5x minus 1 in brackets squared, take away the 3x minus 1 in brackets squared, and we've got to multiply all of that by 45 pi over 360. So that's how we kind of write that and bring that 45 over 360 pi out. That is all going to be equal to the area of B, which is pi times 1 minus x squared. Now, the first thing that stands out to me is that we have an equation with pi on both sides. So we could actually divide both sides by pi, which would eliminate the pi from either side, and that just takes the pi problem out of this question. Obviously, without a calculator, we don't really want to be dealing with pi in these sorts of equations. You've also got that fraction at the start. Now, you might not recognise it straight away, but that definitely simplifies because they end in a 5 and a 0. They actually both divide by 45. So that fraction, 45 over 360, could actually be written as 1 divided by 8. And that kind of gets rid of that and makes that a little bit easier for us as well. So the next step here is thinking about where to go. Now I think no matter what, we're going to have to start expanding these double brackets. I think that's going to be super important for this next step, so let's just go about doing that. Now, depending on how sort of confident you are on expanding double brackets, you might want to write that out in full. Just to save some space, I'm actually going to expand them a little bit quicker. So 5x times 5x would be 25x squared. 5x times negative 1 is 5x, and you'll have two of those. So that is negative 10x. And negative 1 times negative 1 will give you plus 1. Now, I wouldn't advise doing that unless you are super confident at expanding double brackets, but that is just the expansion of 5x minus 1 and another 5x minus 1. And for this one, we're going to do the same thing. This is 3x minus 1 and another 3x minus 1, if you just want to write the working out down as well. And that would be then take away 3x times 3x is 9x squared. 3x times negative 1 is negative 3x, so negative 6x with the two of them. And then negative 1 times negative 1 gives us plus 1 again. And there we go. So there's all of that expanded. We now have the right hand side to expand. So 1 minus x, 1 minus x. Probably not one that I'd advise doing in your head because we've got that negative x in there. So 1 times 1 is 1. 1 times negative x is negative x. We've got two of those, so minus 2x. And then negative x times negative x will give us plus x squared. Right, so everything's expanded, everything's sort of tidied up. We just need to think about what the next step now is going to be. Now, one thing that you could do to make this a little bit easier, we could actually get rid of this eighth. That would just make everything look a little bit tidier. I could times both sides by 8 to do that. There we go, so I could times by 8. That's the same as dividing both sides by 1/8. So timesing by 8, that would just leave me with 8 minus 16x plus 8x squared on the right. And on the left, all we're going to have is what's inside these brackets. But I'm going to actually tidy that up in the same step, obviously, because we've got so many lines to write here. It might just be easier just to tidy that up. So 25x squared, and we're going to take away 9x squared. So 25x squared, take away 9x squared. That's going to leave us with 16x squared. For the next part, let's have a look. We have negative 10x, and we're going to take away negative 6. Now that's one where you've got to be very careful because we are taking away negative 6. So that in essence is adding 6. So we have negative 10x, add 6x, that's going to be negative 4x. So minus 4x. And then for the last one we have plus 1, take away another plus 1. So that's relatively nice for us to do. Plus 1, take away plus 1. and that just cancels out, so we've got nothing there. So here we go, we've got everything we need now. We've got 16x squared minus 4x is equal to 8 minus 16x plus 8x squared. So from there, I need to make that equal 0. So if I make that equal 0, I can probably do that in one jump. Maybe I want to do that in two, but I could probably do it in one jump. So I need to minus 8x squared from both sides. So I'll just write that there, minus 8x squared. I'll work it out in a sec. I need to add 16x to both sides, plus 16x, and then minus 8 from both sides. There's no number over there, so it'll just become minus 8 there. So if we tidy that up, minus the 8x squared, we have 8x squared. Add the 16x, that would give us 12x, so plus 12x. And then take away the 8 from nothing, gives us minus 8, and now it all equals 0, and we have a quadratic that we can actually solve. So from here, you could solve it straight away, or we could try simplifying it first. I'm going to sort of move something out of the way so we can bring this up here. Let's get rid of that. Let's bring our equation up to the top. We'll solve it from there. Okay, so let's go about solving this then. So first of all, I'm going to simplify it. If I simplify that, I can divide everything by 2. So that would be 4x squared. In fact, we could actually divide by 4. Let's not make too much work. Let's just divide this by 4. So that would be 2x squared plus 3x minus 2 is equal to 0. And then we want to factorise that. So we know it's going to have to be a 2x in one of the brackets and an x in the other. Our only factors that we're looking at could be 1 and 2. And we're trying to make plus 3 in the middle. So I want to double the 2 to make 4. And then take away the 1. So plus 2 minus 1, that'll give us plus 4 minus 1, which gives us the plus 3. So we've got one solution in the left bracket there. You've got x is equal to positive 1 over 2, and you've got x is equal to negative 2. And they are your two solutions. So x is equal to a half and x is equal to negative 2. Now there can't be two solutions because it says work out the value of x. It doesn't say work out the values of x. There is only one value here. So let's think about the logic behind it. Now if x is a half, that works in all of those lengths. 2 take away 1 would be the diameter of 1 on the circle B. And for the other sector, 2 times a half would be 1, so it works in the 2x, and 3 times a half take away 1 works in the smaller sector. If, however, you put negative 2 in, it would work on circle B. You'd have 2 take away negative 4, which would be adding 4, so you'd have a diameter of 6, it would work there, but it wouldn't work in here. So 2 lots of negative 2 would give you a length of negative 4, and that's impossible. You can't have a length of negative 4. So you can't have the negative 2, and therefore x equals a half has to be our answer, because you cannot have a negative length. Right, just discussing that, cannot have a negative length. Now with that question, why didn't I just assume that it was the half straight away, as you can't have a negative? Well, as you saw, when I subbed that negative 2 into the 2 minus 2x, that actually gave us a positive length there. And that might have been the case on the sector as well. So the value of x could be negative, as that value of x being negative might actually give us a positive length, depending on what the expressions are. So you need to just test them. So it's obviously always just test the positive one first. If the positive one works, then chances are the negative won't. But it is important to test your answer there, not just assume that because it's come out as a negative number, that means you can't have it. Okay, so there we go. There is another pretty nasty question there. Looking at equations, you had having cancelling out pi, simplifying the fractions, making it all equal 0, factorising and solving, mainly just factorising and solving quadratics there, but it was actually forming them in the first place and sort of linking that back to the sectors and the circles that made that question pretty nasty. But there we go, there's that one. Let's have a look at our next question. Okay, so on to our next question, looking at equations of circles and tangents. Now this is quite a unique question because it's in reverse to what a lot of these questions have normally appeared like. But it says here, C is a circle with centre the origin. A tangent to C passes through the points -20, 0 and 0, 10. Work out an equation of C. So it wants us to work out the equation of the circle. So for this, we need to know what the equation of a circle looks like. We have x squared plus y squared is equal to the radius squared. So this whole problem is going to be working out the radius. If we know what the radius is, then we can write the equation of the circle. So if we think about then what this might look like and think about how we're actually going to go about that. Now I'm going to draw a coordinate grid, which is what I always draw for these questions unless they've drawn it for you, and think about what it looks like. We know we're going to have a circle somewhere centered around the middle, and we just need to find out where this tangent's going to be. So the tangent passes through the point -20, 0. So that's -20 on the x-axis, just over here, so -20. And it passes through 0, 10. So just up here somewhere, let's say that is 10. And then our tangent, I should probably do with drawing the circle first. There we go, that's good enough for me. It's not quite touching the circle there, but it's going to be pretty nasty to draw this perfectly. So there we go, there's our tangent. And our radius is going to be drawn just like this. And we know that the radius touches the tangent at a 90-degree angle. So for this question, if we can work out that coordinate right there, where they cross over, the tangent and the radius, then, the tangent and the radius, then we will be able to find the length of that radius. And we'll talk about that when we get there. But we need to actually find that point. So that's the problem that we have to work out. So this is our x coordinates, this is our x-axis, this is our y-axis. Let's go about figuring this out. So the starting point that we could do here is we can actually find the gradient of our tangent. So our tangent there passes through two coordinates. You've got x and y and x and y. And if you've done, obviously there's different ways that you can approach gradient. You may use the formula y2 minus y1 over x2 minus x1, or rise over run, or however you look at it. But to get here, we have our rise, or our y coordinate, going from 0 to 10. So that is going to be, and let's write that the gradient is equal to, the rise is 10, and the run goes from -20 to 0. Or a run of 20, or a change in x of 20. So that is our gradient, 10 over 20. That is a gradient which we can simplify. That goes down to 1/2. So the gradient of the tangent is 1/2. That's now going to allow us to find the gradient of the radius, because we know that the radius is perpendicular to the tangent. So the gradient of our radius, the perpendicular gradient, will be -2 over 1, or -2. And it is worth labelling these. So that there is the tangent, and this here is the radius. So there we go. Let's have a look at how we're going to do this. So we could find the equation of those two lines, and we want to find the equation of the two of them because we want to find where they intersect. And we had a question earlier where we were looking at intersecting lines. So we need to find the equation of both of them. So let's start with finding the equation of the tangent. We're going to want to write this down. So equation of tangent, and the equation of the tangent is going to be y equals, we know the gradient, where has it gone? There it is, 1/2. So y equals 1/2 x plus the y-intercept. Now the y-intercept we've got for the tangent, it's up here at 10, so 1/2 x plus 10. And there's the equation of the tangent. Next we could find the equation of the radius. So the equation of the radius, there we go, and that is going to be y is equal to, and here is our gradient, so -2x, and the tangent crosses the y-intercept, or the y-axis, at the origin, so that'd be +0, and again when it's +0 we don't need to write that. So we don't need to write that. Let's find where they intersect. So for that intersection point, which we've already got a little cross on there, we need to just set these equations equal to one another. So if we do that, then again we're going to take this part of the equation as they're both y equals, and this part of the equation here. So we have 1/2 x plus 10 is equal to -2x. And it doesn't really matter how you rearrange this. You could move the x's to the left or to the right. It doesn't really matter. If I do move the x's to the left, I'll also have to move the 10, so I may as well minus a half x from both sides. Don't know why I've put divide there. Let's get rid of that. Minus a half x. There we go, minus a half x, and that would leave us with 10 is equal to negative, and let's write out as 0.5, so negative 2.5x. I now want to divide both sides by the negative 2.5. 2.5 fits into 10 4 times, but it's negative 2.5, so x is going to equal negative 4. And that makes sense, because if we have a look back at our diagram, it would make sense that that would drop down on a negative number, so x is negative 4. I also want to know the y-coordinate. If I've got the y-coordinate, then I can start to work out the length of that radius, because I can use Pythagoras' theorem, because we have like a little right-angled triangle there inside our circle, which I've just sort of drawn on. So if we sub that in, we can sub it into either equation. It's probably easier for us to sub it into y equals minus 2x. So for y equals minus 2x, y will equal negative 2 multiplied by negative 4, and that is positive 8. So there we go. That coordinate there is negative 4, positive 8. And that makes a lot of sense when you look at it as well, because it would make sense that that has a height there of 8. So there we go. We have a height of 8, which is the height of our triangle, so that's 8, and we have a run there. I know it goes across to negative 4, but that's a length of 4. So if we draw that triangle to the side, we have a triangle inside our circle that has a height of 8 and a base of 4. And we want to find the length of that radius. Obviously, going back right to the start, the equation of our circle is x squared plus y squared is equal to r squared. So if we know the radius, we just need to square it and put it into our equation. So looking at this, what do we use to find the length of the hypotenuse there? Well, we would use Pythagoras' theorem. So to do this, let's do 4 squared plus 8 squared, and 4 squared is 16, 8 squared is 64, so that combines to make 80. Now you could square root that if you want the actual length of the radius. We don't actually need it though, because look back at our equation, it's x squared plus y squared equals r squared. So to figure that out, we know now that r squared is equal to 80. We don't need to square root it to find the length of r, because our equation is just x squared plus y squared is equal to the radius squared, which is 80. And there we go, there's our final answer. So there we go. A lot of these questions that have come up with equations of circles and tangents have kind of been in reverse. It's almost been, you know, here's the length of the radius, find the equation of the tangent, or something like this, but this was fully in reverse to find the equation of the circle. So there we go, that was a pretty tough question there. A lot of maths. You've got equations of the radius, equations of the tangent using the negative reciprocal. We had solving both the equations simultaneously and then applying Pythagoras inside that to find the length of the radius and eventually plugging that into the circle equation. So loads of maths going on in that one. There's another question for you. Let's have a look at our next one. Okay, so in this question we are looking at rearranging some harder formulas and bounds. So it says here the time period t seconds of a simple pendulum of length L is given by this formula. So the time in t is equal to 2 pi multiplied by the square root of L over g, where L is the length. It says KT uses a simple pendulum in an experiment to find an estimate for the value of g, and here are her results. She's got L as 52.0, correct to 3 significant figures, and t is 1.45, correct to 3 significant figures. Work out the upper bound and the lower bound for the value of g, and use pi is equal to 3.142, and you must show what you're working. So we want to find the lower and upper bound of g, but at the moment g is not our subject. So we want to make g the subject, and then we'll worry about the parts to do with the bounds. So we're going to have to rearrange this. Now the first step to rearrange this formula would make sense that we would divide both sides by the 2 pi. And if we divide by the 2 pi, we get t divided by 2 pi, and that's going to equal the square root of L over g. To unlock that fraction, we need to square both sides. So the next step will be to square both sides. If we square t over 2 pi, well, that's t over 2 pi multiplied by t over 2 pi, you could put that in brackets squared, or we could just square the top, t squared, square the bottom, 4 pi squared. Remember, 2 pi times 2 pi would be 4 pi squared, and that's going to equal L over G. Rearranging from here, again, still isn't particularly nice. We'd almost want to cross multiply these because the G is on the bottom. If the G was on the top, it would be nice. We'd just move the L and we'd be done. But the G's on the bottom. So we want to cross multiply. So multiply the G up to the T squared and multiply that 4 pi squared up to the L. So if we do that, we have, and I'll put the G first, it doesn't really matter, G T squared will equal, and again I'll keep the 4 at the start for this one, so 4 pi squared L. We're almost done. We've just got to now get rid of that t squared. And if we get rid of the t squared, we'd have G on its own. We do that by dividing by t squared. So divide both sides by t squared, and we would get 4 pi squared L all over t squared. Right, there is our formula, finally at a point where we can actually use the bounds, but we've had to rearrange that formula first. So that's the formula we're going to be using. And of course, when we're talking about bounds and we have a fraction involved, we have to think about how we get the lower bound and the upper bounds. So to get the lower bound, we're going to want to have the lowest number on the top divided by the biggest number on the bottom. And to get the upper bound, we're going to want to have the biggest number on the top divided by the smallest on the bottom. So that's just something to remember when we've got fractions involved. Now we need to find the error intervals for these two numbers. And that first one I've just spotted is actually quite a nasty one. So for the error intervals, 52.0 correct to 3 significant figures isn't particularly nice at all. Because if we think about that, L, 52.0 to 3 significant figures is actually in the middle of 52.1 and 51.9. Yeah, 51.9. And we want to find the bounds. So what's in the middle of those? So it is going to go to another decimal place. So in the middle of 51.9, 51 and 52.0, that'd be 51.95. In between 52.0 and 52.1, that'd be 52.05. And there we go, there's our bounds for those. So if we write the error interval, L is in between 52.05 and 51.95. If we do the same for T, T isn't quite as bad, to be fair. Once we've done that one, this one seems relatively straightforward. So that's 1.45, and that is between 1.44 and 1.46. So in between those, we have 1.445 and 1.455. And there we go, there's our error interval that we can write for T. So T is in between 1.455 and 1.445. So there are our intervals. We now pretty much have everything that we want to use in our formula. We just need to remember it does say use pi as 3.142 as well. So when we start putting these in, let's have a look. Doesn't matter which one we work out first. I'll go for the lower bound. So to work out the lower bound of G, G will be equal to 4 multiplied by 3.142 squared, because it's pi squared and it wants us to use 3.142, and the L length that we're going to want the lower bound on top, so I'm going to want to multiply by 51.95, and on the bottom for the lower bound I want the upper bound of what's on the bottom, so the upper bound of T, so that would be 1.455. It is T squared, so all of that squared. Now we want to type that into our calculator, and if we type that into our calculator, we get 969.018164 and there is our lower bound. Moving on to our upper bound, we're going to do the same thing but just plugging in the correct numbers. So for the upper bound for G, that's going to equal 4 lots of 3.142 in brackets squared, multiplied by, this time we want the upper bound on the top, so the upper bound of L, and that's going to be 52.05, so 52.05 on the top, and we want the lowest number on the bottom, again the lower bound there, and that's the lower bound of T, so 1.445, and that is squared again. And that for our upper bound comes out as 984.3677853. It wants us to write them. It doesn't actually say in any sort of amount of significant figures. It just says work out the upper bound and the lower bound for the value of G, and you must show what you're working. Okay, so there we go. So there is our lower bound, 969.018163, and for the upper bound, 984.3677853. Of course, if it did ask us to show our answers to a certain amount of decimal places or significant figures, then we would round them, but this question just says work out the upper and lower bound, so there they are. So there we go, there is a question where we had rearranging harder formulae and also using bounds there. There have been some pretty nasty bounds questions with compound measures that I think maybe just are a little bit tougher than this one, but that did have that rearranging harder formula there with quite a nasty step with the cross multiplication. So there we go, there was a pretty nasty version of a bounds question. Oh, there we go, let's have a look at our next question. Okay, so moving on to one of our last questions. I definitely think that this is probably the hardest out of the bunch, although the next one is pretty difficult as well. So up to you whether you decide whether this is the hardest or the next one. You'll have to let me know what you think. So for this question here, it says that ABCDEF is a regular hexagon. That's the one in the inside there with side lengths of x. So if I put that side length of x on just there, it says this hexagon is enlarged centre F by a scale factor of P to give the larger hexagon. So the scale factor is P. So in other words, each length of the larger hexagon would be px, whatever that number is. If it was a scale factor of 3, it'd be 3x, but it's a scale factor P. So we've got the side lengths of x, it's been enlarged by a scale factor P. Show that the area of the shaded region in the diagram is given by 3 root 3 over 2 p squared minus 1 in brackets x squared. So immediately when you see that, you think, what on earth? Okay, so we have to think about breaking this down in terms of what would we actually do what if we knew the numbers, or it just said work out the area. Well, we would want to work out the area of the larger hexagon, subtract the area of the smaller hexagon, and that would give us the area. So I'm just going to assume that when we do that, we get something that looks like that final answer. And let's just see if we get any pieces along the way that start to look like it. Now, in order to work out the area of a hexagon, you actually have to break it up into equilateral triangles. So what I mean by that is if we split it from each sort of opposite vertice, each hexagon is made up of 6 equilateral triangles. Remember, around the central point there, each point would be 360 divided by 6, which gives us an angle of 60, and the interior angle in a hexagon is 120, and each one is getting split in half here, so that'd be 60, 60, 60, and they are equilateral triangles, all with a side length of x. There you go, we don't necessarily need to draw them all in. So in terms of working out the area of a hexagon, you have to use the area of a triangle formula, which is half AB sine C. So the area of any triangle is equal to half AB sine C. And depending how you look at it, this is actually a relatively nicer version when it's an equilateral, because A and B are the same. So in terms of the side length, or to work this out using what we've got, we have a half. A and B is our x and our x, so x times x is x squared, so a half x squared multiplied by sine 60. And there we go. Now this is a calculator question, so sine 60 is actually one of our exact values, so we could actually replace that with one of our exact values as well. So you could have that as a half times x squared, and our exact value for that is root 3 over 2. So root 3 over 2. Now straight away that might start to link something through to what we're looking for, because if you look at what our answer is, we've got an x squared at the end and we've got an x squared, and this answer here has a 3 root 3 over 2 and we have a root 3 over 2. So that gives us a pretty good indication already from the start, just by using half AB sine C, that we are on the right track, but we just need to figure out what on earth's going on. But we'll get there. So for this one, that is what we have so far. We could simplify those fractions, but I'm going to do something else first. Now the thing that I'm going to do first is, because that was only one of the triangles, and we know that in the hexagon we've actually got 6 of those triangles. So for the area of the hexagon, and let's call it the smaller hexagon, we'd want to multiply the area of that triangle, hexagon, by 6, because there are 6 of them. So we'd have 6 multiplied by our half x squared root 3 over 2. Now that means I can do this 6 times a half relatively easily as well, so that's going to be 3x squared root 3 over 2. And there is the area of the smaller hexagon. I could even incorporate that 3 onto the top. It doesn't matter whether it's written next to the x squared or on top of the fraction. I could actually write that as x squared 3 root 3 over 2. There you go, and just multiply the fraction by the 3 rather than having it stuck in front of the x squared. Now that has given us our 3 root 3 over 2 as well, and we have an x squared. So that is pretty telling that we are on the right track. I now just need to figure out the area of the larger hexagon. So for the larger hexagon, we're not really going to do anything different. If I rub all of this out, which I don't really want to do, because there we go, it was nice and showing us there exactly what we were doing, but if I imagined the larger hexagon, and again I split that up, you have to kind of ignore the smaller hexagon now, but I have exactly the same situation. These are all px this time, as they've been enlarged by that scale factor, and all of these angles would be 60. So I would do exactly the same thing to work out the area of the larger hexagon than we did on the last one, except instead of using x as my side length, I will use the side length px. So if I work out the area of the larger hexagon, I have pretty much the same formula. We have 6 lots of a half times px squared, I'll have to put that in brackets, px squared, multiplied by the root 3 over 2, which is the sine 60. Okay, so we can do 6 times a half, which is 3. Px multiplied by px would be p squared x squared, and then we have the root 3 over 2. Again, if we want, we can drop that 3 on top of the fraction. So if we write that in that way as well, so it matches our other one, we have p squared x squared 3 root 3 over 2. And there we go. That is the area of the larger hexagon. And as you can see, they both obviously look relatively similar. The only difference being is that we have that p squared instead of just x squared on its own. So in order to find the area of the shaded region, we take the larger area and subtract the smaller area. And if we write that out, that gives us p squared x squared 3 root 3 over 2, take away, and our smaller area, which we've got highlighted over there, is x squared 3 root 3 over 2. So that is actually the answer for the area. Okay, we can't actually subtract those away from one another. That is our final answer. But in this question, they've wanted you to write it in a particular way. They've introduced some brackets, or in other words, they've actually factorised the answer. So if we look, what is in both of these things? Well, they both have an x squared, and they both have a 3 root 3 over 2. So we can factorise out x squared and the 3 root 3 over 2. And if we do that, we get x squared 3 root 3 over 2. And if we open our brackets, what do we have left in the first part? Well, we've got a p squared. So in our bracket, that'd be p squared. There's a minus in the middle, so keep that the same. And what do we have left in the second part? Well, that's exactly what the second part is, so we'd have to multiply that by 1. So we get p squared minus 1. And at this point, we've basically matched what it's asking for. The only issue is they've put the x squared at the end. And as we sort of met in different scenarios up here, like at this point, where we moved the 3 to the right on top of the fraction, it's absolutely fine to move these pieces because they're all getting multiplied together. So all we actually need to do is rewrite it as, and how have they written it? 3 root 3 over 2. Then the bracket, p squared minus 1. And then the x squared. And there we go. That's all of that shown. So that is one of those kind of questions where, to be fair, when you look at it at the start, it looks absolutely ridiculous that was going to be our area of the shaded region. But actually all we had to know really was that to work out the area of a hexagon, it was split up into 6 equilateral triangles, and then we needed to know half AB sine C to work out the area of one of them. Multiplying that by 6, our exact values we could actually get from the calculator as well for this question. So to be fair, this would have been a much, I don't want to say nicer, because I think everyone watching this will hate me if I say that, but a much nicer question if it was a non-calculator question, because you actually have had to have known or worked out that exact value on your own. Again, maybe you'd have got an extra mark for that. But there we go. There is our question, and let's have a look at our final question for this video. Okay, and on to our final question. Now this is looking at some sort of geometric proof, also using a bit of trigonometry. It's not a very nice question. The actual solution to this is actually a lot easier than it looks. But on first looking at this question, I can see why people would look at this and just think, no. But it's actually not a bad question. Now in terms of what we are being asked to do, we're being asked to show or prove that AB over BD is equal to AC divided by DC. So we want to involve those lengths, and that kind of looks a little bit like when we're using the sine rule. And we are going to treat this like we're using the sine rule. So if we look at this first triangle, AB is this length here, and if we use a different colour, BD is this length here. And if we were to use the sine rule for those, we would have this side opposite this angle, and this side would be opposite this angle. So we'd need some form of other letter here, let's call that letter Y, just to incorporate this into the sine rule. Now we know when we're using the sine rule, we have A over sine A is equal to B over sine B. And if we plug these values in that we have, we've got AB over sine Y, the one that's opposite that yellow one, and that is equal to, what's our other length, BD over sine X. Now that right there could give us an expression or something that represents AB over BD. So what we could actually do is we could cross multiply these, or sort of flip them around so that they are looking like the way that we actually want it. So let's have a think about how we could do that. So if we rearrange this, we could move the sine X up to here, and that would be AB sine X over sine Y. is equal to BD. And then we'd want to divide both sides by AB. Remember that AB doesn't have to be written on the top of the fraction anymore, it could be just here at the start. And if we divide both sides by AB, I'll leave it up there for the moment, AB, then we would get sine x over sine y is equal to BD divided by the AB. So there's our expression. We have sine x over sine y is equal to BD over AB. Now in our question here, we actually want AB over BD. So we can just flip them both over. So we could write that as sine y over sine x, just flipping both fractions over, is equal to AB over BD. There we go. And there's our first part. So if we can show that AC over DC is also equal to sine y over sine x, then we'll have a match and we'll be able to prove that. But we just need to move on to that other triangle in order to prove that. Now we've said that this length here is y, or this angle here is y. So in order to get this angle here, which is on a straight line, we'd have to do 180 minus y. And that moves us into this triangle. And hopefully that helps us with the lengths. So opposite that is the AC, which is part of what we want there, AC. And on the other side, or opposite the x, we've got the DC, which is perfect because that's what we want just there. So that matches. So let's just take the same approach and see what we get. Hopefully we get something that matches our sine y over sine x. So to do that, again, using the sine rule, they are opposite and they're opposite. So A over sine A, it doesn't matter which way we go, let's just put the AC on top this time. So AC over sine, and we have 180 minus y. There we go. And that is going to be equal to the other side lengths. So DC over sine x. And there we go. If we cross multiply again, so in other words, bringing the sine x up to the AC and swapping the AC back under the DC like we did before, let's just see what we get there. So if we move that up, we get AC sine x over sine 180 minus y, and that is equal to DC. And then we can actually divide those again by the AC. So we get sine x over sine 180 minus y is equal to DC over the AC. Right, again, in our question, we want the AC on the top and the DC on the bottom. So if we want AC on the top, DC on the bottom, we want to flip them over again. So for this one, let's bring it up next to that one. We've got sine 180 minus y over sine x is equal to AC over DC. Right, so at the moment we've got our two fractions there. We've got AB over BD, which is equal to sine y over sine x. We have AC over DC, which is equal to sine 180 minus y over sine x. Now this whole next step, and in order to prove this, you need to understand that sine of 180 minus y is the same as sine y. And you can test this out on your calculator. If you type in something like sine 30, that is equal to a half. 180 minus 30 would be sine 150. And sine 150 is also a half. So this is something you should know from trigonometric graphs. And again, I'll link the video for trigonometric graphs in the video as well, so that you can actually have a look at those. But these values are equal. So any value of sine, if you take it away from 180 and plug that value of sine in, you'll get the same answer for both of them. So in terms of understanding how to prove this last step, you could just say that sine y is equal to sine of 180 minus y. It's just a mathematical fact. They are equal. So therefore, AC over DC is equal to sine y over sine x, which is equal to AB over BD. And there we go. And that'd be a fine proof at the end of that question, showing that they're all equal to one another and got all the same parts for everything. So there we go. That was a very nasty question because there's not really an indication there of using the sine rule. There's not a massive indication that you need to introduce another letter and move between those triangles. But again, that's why this geometric proof stuff is such a tricky topic. So there we go. Hopefully you found that useful and helpful. Again, don't forget, I will link all of the different topics and videos that you need to answer all of these in the description. But again, hopefully that was a good one for you. Don't forget to check out part 1 if you haven't already. There's another 10 brilliant questions in there for you to have a go at. So check that out. But I hope you found this video useful and helpful. If you did, don't forget to like, don't forget to comment, don't forget to subscribe. I'll see you for the next one.